All right, now we're recording, and please go ahead and start when you want. Thank you.
Hi everybody, I'm Nick Grew at I work at the Renewable Energy Lab. I put this presentation together to talk about some of the work we've done in the renewable energy field. And we had the opportunity of using open source tools in order to find the results. And so this is kind of an overview of our process on choosing which tools we'd like to use. And so a little background on myself. I started at NREL in March 2012. Our team usually assists other groups throughout the lab with geospatial analysis support. And so other folks might have certain research that they're doing and they need some kind of geospatial analysis too. And so they come to us and we can provide that support to them. I work on the OpenCarto applications a lot. I'll show you more about what those are in a few slides. And I also work with a team of people developing analysis frameworks. And so there's all kinds of analysis that we tend to do more than once, and a lot of times we do it pretty frequently. And by building analysis frameworks, it means that we can run this analysis and not have to build it from scratch every time to rework the entire.
Oh, come on.
So before that, I worked at the USGS on the US Topo project and graduated from University of Colorado at Denver in 2012. And before that, I spent 4 years in the Marine Corps. A little more information about the National Renewable Energy Lab. As Rafael mentioned, it's in Golden, Colorado. It is a Department of Energy national lab, and there's only 16 or 17 of those throughout the country. And our main focus is on clean energy and renewable energy, doing fundamental research in the fields of clean technologies. Other labs may do some renewable energy work, but we pretty much primarily focus on clean energy technology. And so I'm part of the Strategic Energy Analysis Center, and the Data Analysis and Visualization Group is beneath that, but I'm specifically part of the Geospatial Data Science team. So as I mentioned, the purpose for this webinar was we had work to do converting a desktop-based analysis application to an online version. This desktop analysis software had certain limitations that we hope to address with the online version. And the desktop version itself is starting to become dated. It's been around for 10 years and it's been updated periodically, but as folks are looking for more types of analysis and better hardware to run more complex analysis, we realized we needed to move it out of the desktop-based software and put it online. And so the technical potential analysis is something that we run pretty frequently, and that was part of the desktop-based software that we wanted to bring to the online version. And after trying to replicate the analysis in PostGIS from the desktop version to the online version, we ran into some snags. And so we had to go about some investigation on how to figure out how best to correct results and run a short enough period of time that's acceptable for the users. So just a little background on what technical potential is. Tech potential analysis is basically something that we run to figure out how much energy generation you can get running in building either solar, wind, geothermal technologies, new projects in different areas around the country. And so if you think about if there's a landmark or a national park, you might not be able to build a new wind turbine right smack in the middle of that national park. And so you would, if you're looking like overall all of Colorado, for example, you would know that in Rocky Mountain National Park, for example, you wouldn't be able to build a whole bunch of turbines. And so this analysis kind of removes those barriers and then figures out how much generation you could expect for a given area. And so when you run tech potential, you take the remaining area times the power density of whichever technology you're interested in, times the number of hours in the year, and then the capacity factor for that particular piece of land. And you get back the AC generation, total land area, and the nameplate capacity for that particular piece of land. So this poster is something that we pass around in the lab, and I'm going to zoom up to a certain part, but I wanted to give you an overview of it first. But this particular part of that poster shows the tech potential analysis. And so you can see you start out with a resource potential. So this could be solar direct normal irradiance, or it could be wind speed in meters per second. And you take whatever resource potential you're interested in and add it to exclusions. And so you can see the list of protected areas, urbanized areas, natural features, terrain features. These are all possible exclusions that you might want to apply. And the result of adding these together is a kind of filtered down resource potential data set. And so this tech potential data set can then be used for other analysis, or it's good for visualization. And this is something that we do pretty often here. So when you're talking about tech potential, you might be talking about resource, technical, economic, or market potential. And with this analysis, we kind of cover the resource, technical, and economic parts of this pyramid here. Market goes to a different group here at the lab, and that has more to do with like what kind of, well, as I mentioned, there's what kind of policies are in place for that area, if there's regulatory limits, how interested or how much need there is in a certain area, if you happen to be near a load center, that kind of thing. And so when you're looking at possible exclusions for the resource, the base of that pyramid, you can do resource or generation thresholding. And this just means if you have, for example, DNI, so direct normal irradiance for solar, you may only be interested in areas of land that are 4.0 kilowatt hours per square meter per day up to 7 kilowatt hours per square meter per day. And so by reducing the available area that you're interested in according to resource thresholding, that'll eliminate places where maybe the sun, you're just not getting that much DNI hitting the ground. Generation thresholding has to do with the capacity factor, and so you can limit the available area based on that as well. So for the technical potential, like the actual technical part of the pyramid, you'll look at things like sloped land use, whether or not you're within certain distance of the roads. There's a little bit of overlap here, but these are basically places that will make it more expensive to develop certain projects if you were to build there. Economic has to do with resource slope and land use as well, but here's the distance. You also have considerations for distance to roads and distance to transmission lines. And so if you think about whether you're building close to a transmission line or further away, you're going to need to build new infrastructure to take it to take the energy generation from the project to connect it to the transmission line. And so that'll impact the economic potential. So this is an example of a tech potential run we did in 2012, and actually did a report on it. And so these are all things that were actually part of a publication. So we were considering excluding areas with slope greater than 3%. Contiguous area is actually something you have to consider after all of the other exclusions have been removed. And so if you think about removing areas of land from the possibility of development, you can think about how there might be small little pieces of land that are still available for development, but maybe they're only half a square kilometer. And if you're talking about building a large solar panel array, you're not going to be able to fit all of that in a small piece of land. And so the contiguous area restriction makes sure that you have a minimum required amount of area that you can still develop a large enough project that you're interested in. And so that's what the contiguous area would require. Other exclusions are urban areas, water and wetlands, Bureau of Land Management, areas of critical environmental concern, and there's several others here, including federally protected lands. And so for this particular report, we did exclude places like parks, wilderness, national monuments, but you can, of course, come back and change those inputs to allow more areas for development. That'll, of course, change the results and the downstream analysis as well. And so when you combine all of these different exclusions together, you get back areas that are available, so inclusion areas, and these are places that you can still build in according to this analysis, and then exclusion areas as well. And so looking at this image here, it's a video that I'll play for you in a moment. The purple areas are places that are still available for development. And so this result would go on to a different part of the analysis chain for figuring out, for example, the market potential. The black areas in this image are excluded. And this video will just show you, as you go down the list of exclusions, which areas are being excluded for that particular case. And so you'll see, we'll start off shutting it off so you can see all the inclusion area, and then I'll go step by step showing you how these areas are reduced. So contiguous area, that reduces a lot, and so that you would see this kind of reduction in contiguous area in high slope places. That's because the slope really kind of chops it up. And so as you're going down the list, you can see landmarks remove some areas, land use appear to remove rivers and wetlands, and then slope, because this is a highly mountainous area, removes a lot of land. And that's just because if we have a maximum 3%, anything over that is going to be removed. And so that's where you get that large area of land being removed from consideration. A little background on the geospatial toolkits. So there's a desktop and an enterprise version. The desktop is the one that I told you about, was starting to age and needs to be updated, but it's still useful in the case where you don't have internet. And that was the purpose of developing these desktop GSTs, as we call them. You can either download it from online and then take the computer somewhere where there's no internet, or you can take a thumb drive, which is usually what we do. We bring thumb drives and disperse it to folks during trainings in country. And then you can run the analysis and view the data without any internet. And so if we were going to developing countries, which is usually where we build these for, this is still useful because you can have access to all the data without an internet connection. And so the primary use of the desktop GST, which has some overlap with the online version, is to make these data sets available for analysis and visualization. And so you get this package and all the data is ready to view, and it has all the styles already set up. And so there's very limited amount of setup time. Basically just installing it is what you need, but then all the data is available for visualization, and then you can run the tech potential analysis on it as well. And so when you run the tech potential analysis, you can view the layer in the desktop software, or you can export it to your own geospatial software, either ArcGIS or QGIS, for example. And so as I mentioned before, there's performance issues by having this software running on people's computers, because as you start including more layers for consideration and excluding available area, the analysis becomes more complex. And so if people have relatively old laptops and they're trying to run complex analysis, it's going to take a long time. And that is something that just depends on the person's individual laptop. And so by moving to the online version, we kind of get around that issue, because all the data is hosted here at NREL, everything's on our servers, the analysis is done on our servers. And so rather than putting the burden on individual people's laptops or computers, that analysis and heavy lifting is done here at NREL. And so that was the primary reason for moving the desktop to the online version. And the desktop is still available, but the online version is starting to see more analysis and more opportunity for dealing with large data sets. So when we were looking at doing the technical potential analysis for the online version, we weren't bound by any previously developed methods. There's a certain method for doing tech potential analysis, but it didn't matter how we got there. If we were able to find a better way to do things, then we had that opportunity. And we couldn't do the exact same methods as before because the technology is different. For the desktop version, we use a Spatialite database, which is built off of SQLite, and either did SQL queries in the Spatialite database or use the QGIS API because the desktop GST is built off of QGIS. And so we can't use those same methods online because we're not using the same technology. And so since all of the data for these OpenCarto applications need to be in PostGIS, we thought we might as well just run the analysis there as well using PostGIS and just do typical vector analysis on PostGIS. And I'll preface this with saying that PostGIS is a very commonly used tool here in the GDS team, the Geospatial Data Science team, and it has enormous use. And so I don't want anybody to think that I don't think PostGIS has a place. It's certainly one of the most commonly used tools we have. It's just for this particular problem, it wasn't quite the right tool. And so as we were looking at running the analysis through PostGIS vector analysis, we found some issues with the number of polygons being generated during the analysis and just the speed we were having trouble with. The analysis might finish in a few minutes or a few hours depending on how complex, but some runs for large swaths of area, if the entire country of India, for example, would run on and on and on for days at a time. And of course, somebody trying to get these results through a web browser, that's just too long. And so we started whittling down what the problem was, and we were finding that there's just too many steps when you're doing the PostGIS vector analysis on multiple layers. Anybody that knows running intersection analysis or union or buffer in PostGIS knows that when you do an intersection between polygons, you'll commonly get results of polygons, multi-polygons, and geometry columns, all part of the same data set. And of course, you need to take care of these differing data types before you can continue in the analysis. And so we would find that we'd have to do an intersection between two of the layers, and let's just say that we're considering 5 layers. You do an intersection between 2 layers, then you have to clean and validate and create an index, and then you move on to the next layer. So now you have this combined data set from the first 2 layers, but you have this third one that you need to intersect against as well. So you run that intersection, and then you have to clean, validate, write an index, and all these intermediate data sets need to be written to disk because you're creating spatial indexes on them. And so that, just writing to disk is of course going to take a lot more time than if you're keeping everything in memory. And so as you're going through this, you're just building more and more of these polygons. And so this image here down in the right kind of shows what you would find. You have grids that are maybe the DNI data sets, and then urban areas and wetlands. And then you see the red circles, and those are actually buffers to either cities or roads. And as they expand out, you can see how they overlap, and you just start creating these teeny tiny little sliver polygons. And all these polygons really add up when you're considering 15, 20 different layers. And so even if you were to union all of these up front, you just end up with a really complex data set with all kinds of complex geometries, and all of that needs to be indexed, and everything has to be considered when you're running the analysis. And so it creates a really complex data set that just gobbles up all the time that you're trying not to take running this analysis. And when you're if you were to do a union, if you ever wanted to include a different data set, let's say you have a new data set come in that you want to consider, that will have to be intersected or unioned against this already complex data set. And so that would take a long time just up front before you can even start running your analysis. And so we found that running the PostGIS vector analysis just wasn't running fast enough. If you're doing analysis in the lab here, sometimes it takes minutes, hours, or days, and that's acceptable. But when you're running in a web interface, it has to be a lot faster because people are sitting there and they have their other tabs open and they're maybe checking their Facebook or they're checking their CNN. And they might accidentally navigate away. And so really you only have a few minutes to give back results when you're doing stuff like this through a web interface. And so even taking 10 minutes might be too long. And so by running PostGIS Vector, we were finding that it was just taking too long and we needed to find something that would run faster. So then we moved on to trying to run everything in PostGIS Raster. So Raster analysis has come a long way in PostGIS, especially in the last few updates. There's all kinds of useful tools that look a lot like the vector functions for PostGIS. So you have typical ST intersection, ST buffer. These are the function names, but you can do unions, buffers, dissolves, all the things that you might find in ArcGIS. There's a lot of functions for Raster now that will do similar things. Of course, dealing with Raster is a lot different than dealing with vector, but the concept of these functions are pretty similar between either PostGIS, Raster, Vector, ArcGIS, QGIS. And so the reason we thought that running in Raster would be useful is because with Raster you have the opportunity for real high throughput of data. So rather than having to use spatial intersections to figure out which particular polygons are overlapping other polygons, when you have a raster, as long as you align everything together correctly, you know that one cell in a particular place in one layer is going to overlay on top of another cell in a different layer. And so you get rid of having to do all of that pre-processing before you start doing the heavy lifting of ST intersections or unions or anything like that. By doing the pre-processing up front on the rasters to make sure that they all align correctly and have the same resolution and same ESR IDs, for example, that gets rid of a lot of overhead. And so it also makes the geometries a lot simpler because you're not having to look at vectors that have all kinds of different vertices and shapes. Everything has the same shape. And so Raster will really get rid of a lot of that overhead. And so we found that if we're gonna use PostGIS raster analysis, we had to use ST-map algebra, at least in our thinking for the analysis. And that's because ST-map algebra gives you the opportunity to run multiple bands of rasters at the same time. And so this is, when I was doing the testing, this is the function that I wrote up, and it basically parses out different rasters that you pass into the function and does a little bit of logic on it. And so down here in the middle, you see where it has city dist is pixel, in the first position, and then road distance is pixel in the second position. So these are Euclidean distance rasters. And so these rasters will show you the distance from that cell to the closest either road or city. Protected area is basically just a rasterized version of a vector data set. And so that's a discrete data set where you have ones or zeros, where ones are the presence of a protected area and zeros are the absence of it. And then the return value raster at the bottom is in the fourth position. And those are just the values that you're actually looking to get back. And so the logic happens down here at the bottom. And you can see that if you were looking at a particular pixel, if the protected area raster was a 1, then you know that you can't build there no matter what. And so you can just return null. And so that means that you can't build there. But if it's a 0, then you move on to the next possible exclusion. So you have city distance and road distance. And if either one of those are greater than the limit, then that'll return null as well. But if everything is acceptable and it is within the required distance to either of those features, then you'll get back the actual value. So that's kind of the logic that we would follow running this analysis. And so plugging that function into the STMap algebra function, you're basically just passing in here at the top, you're passing in the position of the rasters, naming the function, and then you have to do these cross joins on the actual raster data tables and making sure that they all have the same tiles. So the rasters in PostGIS raster are tiled up, so you don't have just a single long swath of pixels. They all get broken up into different tiles. And so this is what I was talking about, doing the pre-processing to make sure that the tiles all line up. So you can always expect the first raster to line up, the first raster's first tile to line up with the second raster's first tile, for example. So we found STMap algebra was a lot faster than vector analysis, but it requires that you run a fairly high level code on every single pixel. You can't just lump several pixels together and run it. You actually have to consider each and every pixel. And so as you're going across the certain tile and you're going through each pixel, you're having to do all that logic on every single pixel and every single raster. And so there's just not a lot of performance. There's not a lot of things that you can do to enhance the performance of that. You just have to call this really high level code on each pixel. And the lack of parallel processing in PostGIS means that we couldn't break this up into different tiles and run things concurrently. And PostGIS is starting to incorporate more parallel processing, so that may change things in the future, but at the time we were looking at this, it really meant that you had to go pixel by pixel, and when you're talking about an area the size of the United States, at a 90-meter resolution, you're looking at about 1.6 billion pixels. And that sheer number of possibilities meant that this also just ran too slowly. So there are other functions that you can run that are closer to the actual C code beneath the like the PLPG SQL or Python code. It's a lot closer to the lower level commands and memory, and so this can really speed things up. And certainly ST reclass is much faster than STMap algebra because it is able to run those pixels through a lot faster. But if you're just reclassifying things, you still have a lot of additional processing you need to do, and that's where we ran into trouble. The ST reclass would run fast, but the additional steps after that, that's where we found too much time being taken. And so if you think about running ST reclass, you'll end up with several different rasters all reclassified, but then you need to combine them together. And that's some of the options for doing.
Hello, Nick. We lost you there for a second. Can you hear us? Hello, Nick. Your connection froze.
That's where we were running into trouble.
Nick, can you hear me now?
Oh, yeah.
I'm sorry. We missed you. We lost you there for probably 7 seconds.
Oh, okay.
So can you backtrack a little bit, please?
Sure.
Yeah, thank you.
So once you run the ST reclass, you end up with several rasters have all been reclassified, but then you need to combine them back together. And so you can deal with this either using multiple nested SD intersections, but that gets pretty messy, and there's, you know, some issues with, you know, just data not aligning correctly, or possibly one S3 reclass gave you results that maybe, you know, the S3 intersection wouldn't be expecting. And so it just gets messy, and you have to do a lot of preparation work between every ST intersection. You could convert the raster back to polygon and do typical ST intersections on vectors. But of course, you know, converting in between different data types, that's going to take a lot of time too. And so all these, you know, possibilities, we found that we were still just taking too much time. It was still taking, you know, 10, 15 minutes, even for a smaller country like Bhutan, which is what we were testing on. And when you're looking at large areas of land like India, that's just not going to cut it. So we decided to try out Python and see what tools were available there. And we found lots of open source geospatial tools, either for vector or raster. For vector, these modules include Shapely, Fiona, and GeoPandas. And I'll go into more on these towards the end of the presentation here. But for raster, Rasterio, NumPy, and SciPy were all possibilities. So when you're running things in Python, of course, you can use the multiprocessing modules. So this means that where PostGIS, we were stuck doing one thing at a time. With multiprocessing, we could do lots of vectors at the same time, or lots of raster pixels at the same time. And of course, when you have high performance computers like we do here at NREL, that opens up the possibility of doing really highly parallelized operations, and that would certainly speed things up. If we were to do things in vector, we would still run into the issues of the small polygons. We're still doing the same analysis, just with different tools. And we just knew that running this analysis on all of these small polygons would cause an issue. And so we decided just to pursue raster right off the bat. I like this image here of the vector and the raster because this is actually what we wanted to avoid. We didn't want to, so if we were to use raster, we have to convert the vector data sets to raster, but we don't want to do anything like you can see in the raster image where you're overstating the presence of certain features. And so in the vector image, the lower left corner, you can see there's very little, if any, blue area there, but when it gets rasterized, it really blows up that area, the blue area, and that's just not realistic of what was there. And so when we were converting from vector to raster for the sake of the analysis, we needed to decide on a small enough resolution that would allow the presence of certain vector polygons to still be available and get a good, have the right area and have the right presence, and not overstate or understate things. And so that was something that we had to consider up front. So when we're doing, deciding on the raster analysis, we were looking into these modules, NumPy, SciPy, Pandas, Rasterio, multiprocessing. And all of these were what we were going to end up using and what we did end up using for running this analysis. So I'll just make a quick note on Rasterio. It's a relatively new module, but it really opened up all of this analysis for this method for us. Rasterio sits on top of GDAL, and GDAL itself is written in C and C++, and so it's pretty highly performance tuned package. And GDAL can be accessed by Python itself. You can actually import a GDAL Python module, but Rasterio really abstracts away a lot of the more detailed, finer grained things that you'd need to consider if you were just importing GDAL by itself. So Rasterio just makes it a lot cleaner and easier. getting your raster data into a Python usable format. And so when you're actually reading the data using Rasterio from the rasters, whether it's image files or geotiffs, we ended up using geotiffs, but there anything that can be opened by GDAL can be opened by Rasterio. And so after you read those values into memory, it all goes into a NumPy ND array. And if you have any experience working with ND arrays, the syntax is exactly the same. So if you're used to working with NumPy, pulling raster data in using Rasterio, you're not going to be out of your element. So NumPy is itself good for storing a large number of values. It's already pretty well tuned for performance, and you can run things in parallel on the NumPy ND arrays. The Rasterio itself comes with a command line interface named REO, which allows you to do pretty common GDAL processing. So that may include warp, translate, developing hill shades, resampling things. You can do that with GDAL, or you can do it with REO. REO just abstracts away a lot of the finer grain detailed things that you might have to consider if you're running a GDAL by itself. So going into the processing steps, once we decided on using Rasterio for the raster analysis, we had to create a template raster, because when we're converting different vector data sets, everything needs to line up, and the resolution needs to be the same, and the SRID needs to be the same, and all the projections and everything need to be the same. And so we created a template raster that everything would be based off of, and that's what you need. You need all of the raster data sets to have this same all of these same spatial attributes to get rid of having to do a lot of that overhead, which is what we found doing with PostGIS vector, like making things line up, doing intersects on them on the bounding boxes before we did the heavier lifting intersections or unions. By using this template, it made sure that we didn't have to do those things, because we just knew that everything was going to line up. When you're converting the vectors to raster, rasters can only have numerical values, of course, and so for categorical data like federal lands, which is what is over here in the table, we needed to set up a lookup table for each of these values and be able to keep track of those. And so one study may want to exclude national parks, but another might not. And so we needed to be able to keep track of which values were for which categorical data. And so that's what PostGIS vector ended up doing for us. We kept the vector data sets in PostGIS and used them as raster value lookup tables. Then in the actual interface of the OpenCarta application, so the Enterprise Geospatial Toolkit, our web developers coded up the interface here, and it allows the user to pick any number of different exclusions or specific regions to run. And so you can choose different regions. You can do that resource thresholding, which is the kilowatt hours per square meter per day. You can exclude protected areas, exclude specific land use types. So you don't have to exclude only one land use type. You can exclude all sorts of different categories. You can limit the distance to roads, distance to transmission lines, and limit the max slope. And so all of these go together and go through the analysis and give you the tech potential result. When we're actually running the analysis, the geotiffs and a lot of other raster formats too are actually written to disk in tiles. And so you have several pixels that are next to each other, and they're all going to, they're all part of the same tile. And so if you're using a template raster, which is what we did, all of our different layers would have the exact same shape of these tiles in same position. And this meant that rather than loading all of those 1.6 billion pixels into memory up front, you could instead read just a small, let's say 128 by 128 pixel tile. You just read that into memory and you do the analysis. And this also lets you parallelize things. So if you have several cores that you can be running, if you have 24 cores, you could be running 24 tiles at the same time. And so that will just really speed things up. And NumPy and the array are certainly pretty performant already, but by breaking things up in this way, it really, really makes things cook. You'll just see the speed of analysis really go up at this point. So the reclassification process, we're still doing reclassification just with different tools. You just take the inputs from the user and reduce the complexity of the input raster down to a true false raster. And that's what you see here. If these were slope values and the user wanted everything less than or equal to 3%, anything in the raster that is 3 or less will just be changed to 1 or true. Anything over that will be changed to 0 or false, and this just means 1s are areas that you can develop and 0s are areas that you cannot develop on. So if you have several different land use, several different layers that you're interested in, this is how it might pan out. You'll have slope, land use, protected areas, and they all look different, but then you multiply them together and you end up with this blue raster tile down here, and that's just the combination of all the true and false areas. So if you have areas that are available in land use but aren't available in protected areas, it's always going to be nulled out. Any place that has any of the layers that you input that are not available are always going to not be available in the final result. And so this reduces down the area of places that you can actually develop in. And so taking this exclusion layer, this is the first part of tech potential. You get the technical exclusion. You can multiply that against the actual true values you're interested in, and you just end up getting a filtered results like the table at the bottom. And all of these can be either combined up and joined to a vector table to figure out the available area of remaining, or you can just do tech potential directly on the raster itself. So for the EGST, the Enterprise Geospatial Toolkit Analysis, we actually convert these raster cells into vector polygons again and send them up to PostGIS. And this can all be done with Rasterio as well. Rasterio can take raster cells and combine them into vector polygons. And like is typical sort of behavior in ArcGIS or QGIS or PostGIS, if you have cells that are next to each other of the same value, those will all be amalgamated into the same vector polygon. And so that allows us to do before and after available area analysis to figure out how much area we lost with these given exclusion layers. And so in the actual OpenCarto EGST application, that you can get the tabulated results like you can see here. And this will give you the AC generation, area, and nameplate capacity. And it'll even break it down by, in this case, different regions and states. You also get back a vector layer that you can export out to shapefile and load into QGIS or PostGIS. And these, this gives you the available area given your constraints. And so for this one in particular, it looks like it has a buffer distance to transmission lines and roads, as well as some kind of land use restriction. So this reduces the available area and gives you the available technical potential for the areas with those exclusions applied. So just briefly going over the different modules and software that we used. Rasterio, as I mentioned, reads and writes geospatial raster data sets. NumPy is a really commonly used Python scientific computing module. SciPy NumPy actually combines a bunch of these tools together. So you'll find NumPy is also in the SciPy environment. But then you get things like Matplotlib, Pandas, IPython. All these things are pretty typical scientific computing modules, and SciPy just stacks them all together. PostGIS could probably have its own slide because there is so much to it. It's a spatial index. It adds a spatial elements to Postgres. And so if you have Postgres installed, PostGIS will allow you to deal with spatial objects. Pandas is a high performance, easy to use data set structure for Python. And this was basically the missing link in terms of data frames. So if you look at Postgres, you have something that looks like a spreadsheet. I mean, it's a lot more complex than that, but Pandas basically brings that data frame object to Python, and that really opened up a lot of possibilities for scientific computing. GeoPandas just expands on Pandas. It basically does what PostGIS does for Postgres. It adds the ability of doing spatial operations on a Pandas data frame. And so you can do things like buffers and union and intersection, all those things. That's what GeoPandas adds to the Pandas library itself. Shapely is another module that allows geometric processing, and Shapely is actually what's used in GeoPandas for doing the geoprocessing. So if you think of a data frame or a spreadsheet, one of the columns will have the geometry objects, and those are actually Shapely objects within the Pandas data frame. And so Shapely allows you to do all of these different typical geoprocessing operations. Fiona just reads and writes different GDAL or OGR data sets. And so you can open shape files and export them out to GeoJSON. It just makes it a lot easier dealing with geospatial data sets from different sources. You know, archery is really important for doing spatial indexing. PostGIS allows you to do spatial indexing, and it actually uses archery. So the archery Python module itself allows you to do the same kind of spatial indexing, and that's really important before you're doing, like I said, the heavy lift intersection or union functions, is to run a spatial index on their bounding boxes of the polygons first. And so archery allows you to do that. And just to finish up here, a lot of these modules work together well. Several of them were actually written by the same person, or at least led by the same person, Sean Gillies. He did Shapely, he's doing Rasterio now, let's see, Fiona. So all of these things work together, which makes it a lot easier when you're doing things like what we were doing, where you had rasters as the input and vector as the output. The fact that all of these work well together means that there's a lot less fighting and trying to manipulate the data from one data type to another. And so all of these were incredibly useful for this analysis, and they're all open source, and several of them are right up on GitHub, and so you can just access the source code and push and pull commits and add to the libraries themselves. So just a wealth of good, useful tools here. So I'd like to thank everybody for listening, and I hope this brought you some good background on what we're doing here at NREL and the kinds of tools that we use. And if you're interested in seeing the new online enterprise geospatial toolkits, I listed them out down here. Unfortunately, there isn't a specific landing page for the enterprise geospatial toolkits yet, but you can access them from this links. And if you just want to see other OpenCarto applications like the Wind Prospector or NSRDB Viewer, which shows our solar data sets, you can just reach that at maps.nrel.gov. And feel free to email me any questions and any comments.
Great, Nick. Thank you for that great, very interesting presentation. Very detailed information, very exciting and good experiences. Now, hi everybody that's still joining us here on the webinar. If you can roll your mouse over the interface of the webinar software, you will see the pop-up menu at the bottom, and then you have a chat option. So if you have a question or a comment, you can please use the chat, and I will be able to see it and read it for Nick. So to give you a little bit of time to type something, I would like to ask you a quick question, Nick. Predominantly in your formation in the university, you were predominantly trained in proprietary software, ESRI products, remote sensing, proprietary software. What do you, then you went out there and in a very short period of time, just 4 years, you have become this level of abilities and performance using open source software. What do you consider were the biggest hurdles that you had to overcome to start using open source software tools? Was the documentation, lack of training, or what was your experience?
Yeah, I think having a good background of the spatial concepts was really useful, and I got that studying ArcGIS, of course, but I think the hardest thing was learning the programming language. That was really something different. I hadn't really experienced anything like that before, and so suddenly being launched into an area where I need to either do, for PostGIS, SQL coding, and for Python, just writing the code for Python, that took a good amount of work. And so I think having a background in the geospatial tools and methods was really useful, because that might not have been something you could find online as easily. There's all kinds of different resources online for learning coding. And so I think if you can either study it in school, either Python or SQL, if you study that in school, that's great, but there's a lot of online resources like Code Academy, Learn Python the Hard Way is another one. These places really just give you the basics of learning the Python code. And then really it's just about jumping in and trying to figure out how to make the code do what you want. And there's all kinds of trial and error and searching websites like Stack Exchange, Stack Overflow for questions that other people have answered really speeds things up, so that you're not necessarily trying absolutely everything for the very first time yourself. There might be somebody out there that has done the same, that has tried to do the same things and found a way to do it, and maybe they could help you along a little bit faster than if you just started from scratch.
Excellent, thank you. There's a question here. Is it possible to have access to some of the code that you have written for the applications that you demoed?
Yeah, there's an NREL GitHub website, and I'm not sure if this code is there, but yeah, there's some things that maybe have to go through, the people here that check proprietary information, that sort of thing. But yeah, there should be a way to get to some of this code. I might have to get back to you on whether we can upload that to our GitHub page or not. But there's already different projects on the NREL GitHub page that are worth checking out. And there's a lot of Python, Ruby, and other different languages up there as well.
Excellent. Here there's a quick comment that says, there are disadvantages in using square rasters. If anyone is interested in why hexagon rasters are superior, send a message to capeblanco@peak.org, and I will send a presentation. And this is from Dennis. So it's a quick comment about that there might be some disadvantages on using square rasters. And now we're using hexagons. Yeah, I have heard about that in other contexts for climate change. Do you have any comments about that, Nick?
I mean, we're always interested in new technology, and there's all sorts of land use problems that we're trying to deal with that use the Python module. I think it's called Land Lab, and that's uses. I think it might not use hexagon, but it's a kind of built up raster data set that allows for figuring out things like fault scarps and things like that. And so, yeah, we're always looking for new tools and different ways to do things to make our analysis better.
Yes, awesome. And again, the point of contact for Nick is in the last slide. We are going to post these slides and recording in the Geo4All website webinars page, and they will be available there for you. Any other questions that the audience might have at this point? I don't see any other ones. And we are right on time, perfect, 12, it works perfect. So again, I think you left us with very good information that we can chew on and then get back to you. And we really appreciate your time and sharing your knowledge. And probably you will be hearing from more people once we post these on the YouTube channel of the Geo4All Labs.
Great, sounds good. Yeah, I'm looking forward to it.
All right, thank you, Nick. We'll see you. Thank you, everyone, for attending, and we'll see you in the next webinar session. Bye-bye, all.
Bye.